The East Coast, apparently an hour south of Halifax. He did his master's and a PhD at Dalhousie, worked with Randall Martin, and has continued to work in Halifax, now with Environment and Climate Change Canada, specializing on satellite-based observation. And today he's going to share some of his findings in terms of how ambient NO2 changed around the world due to the lockdowns that are associated with COVID-19. So with that, I'm going to pass it over to Matthew, and let's all virtually give him a big round of applause, which he won't hear, but the emotion will be there. So over to you, Matt.
I appreciate the sentiment of applause, even if I can't hear it. Yeah, so I am at Environment Canada now, but this is all work that I did during my postdoc at Dalhousie and at Washington University in St. Louis, where I was working on using satellite observations of NO2 to look at fine scale spatial distributions of ground level NO2 for air quality analysis, and then applying those to looking at the changes that we saw during COVID lockdowns. So we know that NO2 is a really important air quality hazard, that people that live in places that have high NO2 concentrations experience higher rates of asthma, respiratory disease, and greater mortality rates overall. On top of that, NO2 is a really important precursor gas in the atmosphere, and that it leads to ozone production, and it leads to the production of nitrate aerosols, which contribute to PM2.5. And recent studies from Health Canada have shown that there's roughly 15,000 deaths every year attributed to air pollution from ozone, PM2.5, and NO2. And NO2 on its own is a smaller portion of this, but again, as a precursor to ozone and PM2.5, it really is playing a role in all of these. The main source of NO2 is, of course, the burning of fossil fuels. And most of the NOx in Canada is actually coming from the transportation sector. In fact, NO2 is so strongly linked with transportation emissions is that it's usually used as kind of a tracer for transportation emissions as a whole. And so we consider kind of NO2 to be the transportation pollutant indicator. An interesting thing about NO2 as a pollutant is that it has a relatively short lifetime. Tropospheric NO2 typically lasts for about a day, meaning it doesn't really get transported very far from where it's emitted, and it makes it a really good indicator from local pollution sources. So these are some figures from Dan Goldberg's paper looking at TROPOME satellite NO2 columns around the Toronto-Hamilton area on the left and around New York City on the right. And you can see that there's some really sharp spatial gradients where in the downtown cores of the city, the concentrations tend to be very high, where you have a lot of traffic, and then they kind of fall off relatively quickly as you get away from those sources because of that short lifetime. The other thing about a short lifetime is it means it can respond really quickly to changes in emissions, which is going to be the main topic of the later part of this talk. And emissions have been changing over the last several years. We've been seeing steady decreases. This is from the CCME air quality report showing concentrations in Canada have been decreasing over the last couple decades. And this is thanks to air quality policies, but also technological advances like better technologies on power plants and catalytic converters in cars and things like that. So NO2 has kind of been steadily decreasing, which is really good news. Because we know that NO2 has these important health impacts. And we know this thanks to a lot of really good studies that have shown the relationships between NO2 exposure and health outcomes. And these studies are often based off of ground monitors that measure NO2 in a city. And these are very useful tools for measuring NO2 exposure in the vicinity of these monitors. But we know that there's a lot of places around the globe that don't have adequate air quality monitoring at the ground level. This is a figure from the OpenAQ project that's showing the location of publicly available ground monitor NO2 data around the globe. You can see in places like Eastern China and Europe and the urban areas in North America, we have pretty good monitoring network. But in places like South America, Africa, and the Middle East, South Asia, there aren't really a lot of ground monitors available. And that really makes it hard to understand what the exposure is in these areas. But even in places where we do have ground monitoring, like in urban areas in North America, these ground monitors can't really capture all the variability that happens in NO2. So this is a figure from a study where they put a NO2 monitor on a car and drove it around Oakland. And you can see that the NO2 concentrations vary quite a bit across the city scale, much higher when you're closer to the roadways, lower when you're a little bit further away. And so even if you were to have a couple ground monitors in this city, if you were lucky, that's still not going to capture the variability that happens there. And that too is going to impact our ability to understand the exposure and impact health studies. Satellites are really useful for filling these gaps because a satellite can observe the global spatial distribution of NO2 in a way that a surface observation couldn't. So this is a really great map showing tropomi NO2 columns over a 6-month period in Europe. You can see how the major cities really stand out as being large NO2 hotspots, but you see a lot of smaller cities kind of popping out too. You can see these shipping tracks through the Mediterranean and along the coast. You can see things like highway routes, like running between cities. And so satellites can give this really good spatial information about how NO2 is varying. And you'd never be able to get this from a surface monitor alone. So these can be really useful tools. And tropomi, which has been, all the satellite pictures I've shown so far have been from the tropomi instrument. It's been really groundbreaking in terms of its ability to observe the spatial distribution of NO2. And I want to highlight this by showing this figure here that shows 1 day of observations of NO2 over Europe from tropomi, and that same day is observed by its predecessor, OMI. OMI was kind of the previous gold standard for satellite NO2 observations, and it's been providing really high quality data since 2005 and it's been used very successfully in a lot of health impact studies. But the OMI horizontal resolution is much coarser than what we now have from tropomi. And so you can see that this higher resolution information offers the ability to monitor NO2 air quality in a way that is much better than what we could do before. And there's even future upcoming missions like the geostationary constellation, including TEMPO, that's going to offer even further improvements. So the future is looking even brighter for monitoring from space. I've kind of passed over so far is talking about these being satellite column observations. And the reason why this is important comes to how these satellite observations actually work. So the way these satellites are monitoring NO2 is you have sunlight that's coming through the atmosphere. It's reacting with gases, particles, clouds, the surface, and it's being redirected back towards the satellite. The satellite has a spectrometer that measures the observed spectrum of light, and then because we know what wavelengths NO2 absorbs at, we can work out how much NO2 that light encountered on its path through the atmosphere. And so that tells us basically how much NO2 is in a column of the atmosphere that the satellite is looking at. And that's really useful because it provides this really nice, these really nice maps showing the column of NO2. But from an air quality perspective, what we want to know is not how much NO2 is in a column. What we want to know is how much NO2 is at the ground level where all the people are living and breathing. So we need to be able to convert that column concentration into a ground level surface concentration. You could do that if you know what the vertical profile shape of NO2 is in the atmosphere. And for this work, what we do is get this information from a model. And we use the GeosChem chemical transport model, which essentially breaks the atmosphere into a grid. And you provide the model as input the meteorological conditions and the NOx emissions. And then the model moves that NOx around, it does chemistry to it, does scavenging and deposition. And from that, we can get vertical profiles of NO2. And I'm showing here in this figure some examples of some typical NO2 profiles. And these are normalized profiles, so they sum up to 1 just for comparison's sake. Well, what we see is that the shape of that NO2 profile really depends on what the conditions are locally. For example, if you're in an urban area where you have a lot of traffic emissions, most of that NO2 is going to be down near the surface because you have this really large local emission source that's providing NO2 at the ground level. As you get to a more rural area, these urban plumes travel downwind. They get a chance to mix throughout the troposphere and typically have this blue profile shape that's more, uniform vertically. And then as you get even further downwind, to a more remote region, that NO2 down near the surface, maybe it's been converted to aerosols, maybe it's turned into nitric acid and been rained out. You can get really low concentrations in the lower troposphere. The lifetime's a little bit longer in the upper troposphere, and so you can actually have cases where your NO2 concentration is higher at the upper altitudes than it is down at the surface. So you can see that if you wanted to take a satellite observed column concentration and tell you how much NO2 is at the surface, the shape of this profile can be very important. And luckily we have a model that can give us this information. But one problem is that our models are typically at a much coarser resolution than our satellites. And in this work, for example, we're going to use tropomi data that we've gridded to 1 kilometer resolution. And we want to estimate surface concentrations at 1 kilometer resolution based off this, but our global chemical transport model is at a 2 by 2.5 degree resolution. So that's orders of magnitude larger. And that poses a problem. So what we need to do is have a way to downscale this model information in a way that can provide constraints to this higher resolution satellite info. And what we do is use information from the satellite observations themselves to help us do this downscaling. And the first component of this was developed in this paper from our group at Dalhousie back in 2010, where in this Lamsol paper, they developed a method of downscaling the horizontal information in GeoSChem. So you begin from a GeoSChem model grid box. Of course, the model provides one single value for that grid box, but we want to know how NO2 varies within it. So what we can do is take our model grid box, break it into smaller subgrid pixels, and then use the satellite to observe how much the concentration in one of these subpixels compares to the average concentration across the whole grid box. We can produce a scaling factor, and then by applying that to our GeoSChem grid box, we can get a downscaled version of the model, where if the satellite says there should be a little bit more NO2 here, we increase it there and then kind of decrease it there, and shift it around according to how the satellite sees the variability in that grid box. So that's how we can horizontally downscale the information. In an update to our algorithm in 2020, we introduced a new constraint from the satellite on the shape of the boundary layer profile, because most of the variability that's going on in this grid box is going to be happening down in the boundary layer. And we know that if you have a really large surface pollution source, then you will have a boundary layer that's more highly concentrated down near the surface. And if you're downwind from these large pollution sources, then you typically have a boundary layer that's a little bit more well mixed. And so what we do is use the satellite columns within these subpixels. And if the satellite column is low, we assume a well-mixed boundary layer. If the satellite column is high, we assume this. And then if it's in the middle, we kind of do a linear interpolation between those two cases. And so now we have a way to downscale the model's horizontal information and the vertical information in a way to better represent the shape of this profile. This is kind of a summary of what happens when you do these different approaches. So I'll draw your attention to this top right panel first. This is an example of what the OMI inferred surface concentrations look like at 10 by 10 kilometer resolution, which was this method developed in this Lamsol paper, where they use the horizontal downscaling, but without the vertical boundary layer profile downscaling that we implemented later. And by using this approach, we can get maps of NO2 that look like this. And so this is the eastern United States and southern Ontario. And you can see that from these OMI pixels, which again are coarser resolution than our new tropomi instrument, we can get these pretty reasonable looking maps where you see major hotspots like New York, Toronto, Chicago standing out pretty clearly, broad regional enhancements over other generally urban areas. But when we make comparisons between this method using OMI and ground monitors, we typically saw a pretty low bias. And it was thought that the bias was because the pixels in OMI were much coarser, and that if we had a satellite that had a finer resolution, then that should resolve that problem. And to some extent it does, because when we use this same method, but the finer resolution observations, then we do get a better slope. We improve the correlation quite a bit, but we're still biased low. And it turns out we needed to add this secondary constraint on the boundary layer profile to really leverage this high resolution satellite data in the best way. So when we add this new boundary layer profile constraint, we get a much better agreement with the surface observations and a really good correlation, and we can produce maps that look like this. So this is the same area, but using tropomi observations and our updated algorithm, we can get a map of NO2 concentrations at 1 kilometer resolution. And you see, like, in a broad sense, it looks very similar to this one, but because we now have these fine resolution observations, we can better observe spatial structure. We see sharper gradients in NO2 because we've resolved this bias by implementing this additional constraint on the boundary layer profile. We see the concentrations are generally higher in this estimate, and you can see the hotspots around New York, Chicago, Toronto that we could kind of see before are much more pronounced. And we can now see smaller cities like Philadelphia or Washington standing out quite clearly. You can see it now, because we have this high resolution satellite information, we can see things like highway routes kind of clearly going across some areas. So we can get these really nice pictures of NO2 distributions. And because our new updated algorithm has reduced this bias, and because our satellite observations can now better resolve the spatial gradients, this impacts our exposure estimates that we can produce. So in this figure, we're looking at the first, this is the NO2 exposure in North America over the first year worth of tropomi observations. And the tropomi exposure estimates in red, and the dashed lines represent the old algorithm. The solid lines represent the new algorithm. We can see that because we've fixed this bias and we're resolving the spatial distributions, we end up with having higher exposure estimates. Whereas we're seeing, comparing OMI and tropomi, 3 times more people exceeding the Canadian air quality standards across North America. And extend this algorithm globally, and we can produce a map like this. So this is the 2019 annual mean surface NO2 concentration globally at 1 kilometer resolution. So this is really high resolution estimates that have not been produced from previous satellite-based estimates. And we can see quite clearly, major hotspots, particularly in Eastern China and India, urban areas in Europe and North America and other places around the globe. We can make comparisons between the ground monitor data that we have. There's really good ground monitor data in Europe, North America, and China that we made comparisons between. And here I'm showing a comparison between our satellite-based estimates from tropomi and the ground monitor data in those regions for monthly mean estimates instead of annual mean, and we still see really good agreement between the ground monitors and our tropomi-based estimates. And if we compare the seasonal cycles of these two, we see good agreement there as well. And so this goes to show that we can get a pretty accurate representation of ground level NO2 with a 1 kilometer resolution. And we're doing this using a model that is at 2 by 2.5 degrees, which is really remarkable that we're able to get accurate estimates at such a high resolution, even though our model resolution has been lagging behind. So while tropomi is very useful at providing this fine scale detail, we only have tropomi observations going back to 2018 when it was launched. If we want to know something about long-term exposure, it'd be nice to be able to leverage some of this long-term data we have from OMI, but still retain this high-level spatial information we get from tropomi. And so we've combined these two pieces of information to get a long-term high-resolution data set in this way. We start from our annual mean OMI columns, and years worth of studies of OMI NO2 observations have shown that you can get a good map of OMI NO2 for an annual mean at a roughly 10 by 10 kilometer resolution. If you go much finer than that, then the maps start getting a little too noisy. But this is an idea of what that looks like. So this is OMI NO2 columns at 10 kilometer resolution for 2015 in California. So we have, this is San Francisco up here and LA down here. And so you can see the broad enhancements across these urban areas. If we compare the OMI columns to the tropomi ones, you see tropomi sees the same kind of hotspots, but we have much more spatial information. We see sharper spatial gradients at tropomi because we can regrid it to a finer resolution. So this is kind of a 2-year average of tropomi at 1 kilometer resolution. So what we can do is create a scaling factor based off tropomi. So we take our 1 kilometer tropomi, regrid it to 10 kilometers, and apply that to the OMI one. We can now get kind of a downscaled OMI column estimate for 2015, which still maintains the broad features of the OMI map, but with some of the fine scale structure that we were able to observe from tropomi. And so by doing this throughout the whole OMI time series, we can get a high resolution estimate of NO2 columns back to 2005, which we can then use to estimate the surface concentration. And here's an example of the impact that this downscaling has. On the left, this is the San Francisco Bay Area. If we had used our method of inferring the surface concentration from the satellite observations using OMI at 10 by 10 kilometers, we typically see kind of a broad enhancement across the region with very little spatial variability across that. If we use our downscaled columns, the OMI tropomi combined product, we can grid this at 1 kilometer resolution, and now we can see the fine scale structure a lot more clearly. You can distinguish Oakland from San Francisco, from the airport region, from San Jose. So we have this fine scale structure that allows us then to take this back in time to 2005 to look at how NO2 exposures have changed over the 15-year time period that we looked at a high resolution. So this is a map here of the trend in NO2 globally going back to 2005. The way you interpret the color bar here is that blue means NO2 is being decreasing, red is increasing, and the kind of saturation of the color represents the statistical significance of that trend. So a dark blue trend is more significant than a light blue trend. And so what we see is that, particularly in urban areas in Europe and North America, some places in Asia, we see significantly decreasing trends in NO2. We can make comparisons between our satellite-based estimates and the ground monitors that we have. For Europe and North America, we have ground monitor data that goes back to 2005, and across the whole time period, our satellite-based trend in red agrees really nicely with the ground-based one in black, and in both Europe and North America. In China, we had available ground monitor data back to 2015 only, but over this short time period, our trends agree pretty well. And we'll note that in China, over this time period, the early stages, NO2 is generally increasing, kind of plateaus around 2012, 2013, and then starts decreasing afterwards. We didn't have available ground monitor data in other places in the globe, but we see kind of similar thing that we see in China, where in South America, Africa, and Oceania, the early stage of the time period, generally NO2 is increasing, and then at some point it shifts and starts decreasing. Although the point at which that shift happens varies by region. But we're able to get these really nice, again, high resolution, 1 kilometer resolution estimates of the NO2 trend back to 2005. And so that's to take a second here to kind of summarize this first half, where I just want to talk about this algorithm that we've developed. And so we're able to get these high resolution maps at 1 kilometer resolution to estimate surface NO2 concentrations from satellites. And that these can be really useful to fill in the gaps between ground monitors and inform on regions that we don't have them. And all this data is publicly available online and can be used in any sort of health study that you feel like using it for. And now for the rest of the talk, what I want to do is talk about a way that we've used these observations to look at how NO2 concentrations change during COVID lockdowns. Now, this was a very common topic of conversation in our community in early 2020, where qualitatively, we kept seeing these reports of places like Delhi, where air quality is typically very poor, but during the lockdowns, when schools and businesses were being closed and transportation was being limited, the air noticeably cleared up. And then we have things like satellite observations of NO2 columns over China, This is from NASA, where we see before the lockdowns, your typical scene of high NO2 concentrations in many places dropped off quite dramatically. And so, again, these satellites are really useful for showing this distribution, but we want to know what the ground level NO2 looked like, not just the NO2 columns. And so that's where our data set becomes very useful. This is some figures from a 2020 paper looking at changes in CO2 emissions. And I show this to demonstrate a couple important points here. And that's that the effect that a lockdown has on your local air quality depends a lot on where you live. So for example, the timing of the lockdowns obviously is very different. In China, the lockdowns happened much earlier than other places in the globe. But across the globe, most emissions inventories have shown that emissions seem to have decreased in 2020. And this kind of breaks it down by sector. And of course, the sector where we saw the biggest changes is in aviation. There wasn't a whole lot of travel going on during this time period. And so we saw really large decreases in CO2 emissions over that time period, and big changes in ground transport, some smaller changes in power generation industry and residential. And again, I just show this to point out that your local air quality is going to depend on which one of these sources is contributing the most to your local air quality and how sensitive these different industries are to lockdowns. And so again, this was a really common topic in 2020. If you do a Google Scholar search for COVID lockdowns and air quality, you get tens of thousands of hits. There's a really good review paper published last year that looked at the 200 or so papers that were published in the first 6 months of the pandemic. So like people were really on their ball and getting this research done quickly. And this figure comes from this review paper where they take the observed changes in NO2 and kind of broke it down by region. And what we see is that consistently NO2 concentrations were lower during the lockdowns in 2020 than they were in 2019. And this has been reported on by dozens and dozens of studies. But what's interesting to me is that a lot of these studies are missing some important context. For one, we've said that in a lot of places around the globe, NO2 concentrations have been going down over the long term. So I think it's important to look at how the change in 2020 compares to what the long-term trend has been. And the other thing is that a lot of these papers were missing some context about meteorology, because your concentrations of NO2 can vary quite a bit if your meteorological conditions are different. And this histogram here shows that most of these papers either didn't discuss the impact that meteorology has on NO2 at all, or mention it in passing without really trying to quantify it at all. And I think that's really important context that should be considered. The second thing here from this review paper is it points out that most of these studies are based off of ground monitor data, which is very useful for understanding how NO2 changed wherever that ground monitor is, but doesn't tell you much about the spatial distribution of NO2 or what's happening a couple of kilometers away from that ground monitor. So they either focus on those ground monitors or they use satellite tropospheric columns, which again provide that horizontal information, but are not exactly analogous to a ground level NO2 concentration. And so luckily our method of using a satellite derived ground level NO2 concentration can kind of bridge both of those gaps. So that's what I'm showing here. This is the global 1 kilometer NO2 change from April 2020 to April 2019. And what we see is, especially in a lot of the urban areas, very large decreases in NO2. But we also see a lot of spatial heterogeneity. Some places had really significantly large decreases, some had smaller changes, some areas were even higher. And that's where we want to start considering some of these contexts that I mentioned have often passed over. So let's start with these long-term trends. The maps that I'm showing here are kind of in two columns. On the left column, I'm showing the surface concentration as inferred from Tropome using our method, comparing 1 month in 2020 to that same month in 2019. The month that we selected is kind of shown on the side, and you'll note that the month is different for each one of these regions based off of when that region had its largest lockdown. And then the right column is showing our long-term trend. So over the time period given, what is the kind of typical year-to-year change in NO2 according to our satellite-derived trends? And again, I'll note that I chose a different time period in different regions based off of when the trend was most consistent, because some places during our whole time period were increasing at the start and then decreasing after. We really just want to focus on the area where it's, monotonic. So what we see here, and the numbers on the inset are the change in population-weighted NO2 over that domain. So we see that most of these places around the globe have had NO2 concentrations that have been decreasing over the long term. Particularly if you look at China, NO2 concentrations have been dropping really quickly there. And you can see a lot of areas where the decrease has been pretty large. But in all of our areas, we see that the actual change in 2020 is much larger than what the typical long-term changes have been. So while the long-term trends range from about 1% per year to as much as 10% per year in China, our actual observed changes are up to, over 40% in Europe, 20% in North America. So our observed change in 2020 was much larger than the long-term trend. This table here compares what the actual long-term trend was in these areas to what the actual observed change was in these areas to the long-term trend in terms of how many years worth of change did we see in 2020. And globally, we see that the change in 2020 was the equivalent of 15 years worth of incremental decreases thanks to technology improvements and things like that. So the change in 2020 was dramatically larger than our long-term trend by an order of magnitude. Next, I want to consider these meteorological effects. So I said this briefly, but there's actually two ways that meteorology could impact our analysis. One is that if you have high wind speeds, high boundary layers, then your pollutants can disperse away from their emission source really quickly. And so it's possible that by comparing April 2020 to April 2019, you could see a difference just because the weather conditions are a little different. On top of that, the weather can impact our ability to monitor that NO2 from satellites, because satellites can't see through clouds, and satellites are affected by snow cover. And so maybe you see a difference from one year to the next, but it's just because one year was cloudier than the other year. So it's important to figure out the impact that that has as well. So to do that, we use our GSChem chemical transport model to try to account for these changes. So these figures are similar to the last slide, except now on the right-hand column, I'm showing the GSChem simulated change from 2020 to 2019. Because we give GSChem as an input the meteorological conditions, so it knows what the weather conditions were, but it doesn't know that there was a lockdown. So whatever change we see in our simulation is the change that would have happened if there was no lockdown, just because the weather conditions were different. And you can see that in some places this is pretty significant. Like there's some significant decreases in Eastern North America, parts of China, across Central Europe, where we do see large changes in NO2, like a 10% decrease in NO2 would have happened anyway, even if there weren't any lockdowns. But if we start comparing these meteorological changes to what was actually observed, here I'm regridding Tropomi to match the resolution of the model. We see that although it would have decreased in most of Eastern North America anyway, the changes that actually happened in Toronto and New York, for example, are much, much larger. Same for China, we would have seen decreases here anyway, but much larger in practice. And so what we can see is that, yes, meteorology can be very important locally, but in general, the observed changes in all of our regions were much larger than what we would have expected from meteorology alone. So there really did have to have been some large changes in emissions during this time period. Next, we wanted to look at the idea of if you had a stricter lockdown, does that mean you would see a bigger change in NO2? So the way we went about looking at this was for each country and each month from January to June, we took the country level population weighted NO2 concentration and compared that value for 2020 to that value for 2019. Then we took information about the stringency of a lockdown, which was collected by a group at Oxford in this COVID-19 government response tracker. What they did was they had a list of policies that they were checking in each country and produced a scale that went from 0 to 100. And so for each day since the beginning of the pandemic, they provide a value of 0 to 100, where 0 means that country is operating business as usual, and 100 would mean complete shutdown of everything. And then we made this histogram here showing the change in the country level NO2 concentration in the months that had the strictest lockdowns, which are plotted in red, and the months that had the weakest lockdowns, which are plotted in green. You can see that this red distribution is shifted to the left, meaning that in general, our NO2 concentrations were lower in 2020 if your country had a strict lockdown. And in fact, the mean ratio is about 30% lower if your country had a strict lockdown than if it didn't. And I'll note that, it's possible that you could have a strict lockdown and still see NO2 go up. And it's possible that you could have no lockdown and still see NO2 go down. Because meteorology is important. But on average, the peak of this distribution for no lockdown is 1, indicating that, if you have no lockdown, you on average didn't see much of a change from 2020 to 2019. Whereas if you do have a lockdown, typically your concentration is much lower. This figure on the right is kind of another way of showing this same data. Here, every point in this graph is one country for the month that they had their strongest lockdown, as indicated by the color. And then we're looking at how the stringency of that lockdown compares to the change in NO2 that they saw. And so we can see that if you had a relatively weak lockdown, you had much smaller change in NO2. If you had a strong lockdown, much larger changes. Excuse me. Okay, so more on country level NO2 changes. Here's a figure where each row represents a different country. And this first column here is the observed change in NO2 according to our tropomi-based estimates. The middle column is the expected change because of meteorological conditions, and the third column is based off the long-term trends in that country. You can see that in all of these countries, we have a blue color indicating that NO2 concentrations decreased, and on average, this is a 35% decrease. Canada clocks in at around 31% lower for April in 2020 than 2019. If we compare the observed change to the expected meteorology, we see that some places would have had decreases anyway, but typically those changes are much smaller. The average meteorological driven change was around 3%. Same with our long-term trend, the average decrease is about 3%. And that goes to show again that at the even country level, our observed changes were much larger than would have been expected from either meteorology or the long-term trends. Then we can zoom in even further. Instead of looking at country levels, let's look at individual cities. And so I chose 215 major cities worldwide. And so now this figure is the same as the last one, where each row instead represents an individual city. You can see there's a little bit more variability when you start looking at smaller spatial scales, but 87% of the cities that we looked at had lower concentrations in 2020. And for 65% of those, the change was by 25% or more. The histogram here kind of summarizes these different lines. The red shows the observed changes in NO2. So you can see generally most cities saw some pretty large decreases in NO2. The green shows the expected change in meteorology, the blue from the expected long-term trend. You can see that on average, our cities saw about a 32% decrease and would have expected about a 1 or 1.5% decrease because of meteorology or the trends. So again, the observed changes are much, much larger. So I'll just pause a second here to talk about why this is important, because we say that these tropomi-derived estimates are very useful for filling the gaps that are missing in the ground monitor data. So these box and whisker plots here show the distribution of the observed change in NO2 in various cities worldwide. The top one shows the results from this review paper, where there were 79 studies that had ground monitor data, representing 381 different ground monitor measurements. And this is the distribution of those changes. We see that the median change is around 30–35%. And we compare that to the changes in the 215 cities that we looked at in our work. We see the distribution is relatively similar. The median's around the same. We typically are around 15–20% at this edge. So very similar distribution, meaning that our tropomi-derived estimates are broadly consistent with the other ground monitor-based studies, which is good. But we can break our data set into cities that were included in this review, indicating that these are cities that have ground monitors that were looked at, or cities that were not in this review, indicating there are cities that did not have ground monitors. And we know, and if you look at the distribution, you see they're pretty similar. You know, the medians are very similar, the range is very similar. So it shows that even if you don't have a ground monitor, that doesn't mean that NO2 didn't change during lockdowns. It doesn't mean you didn't have a lockdown. It just means that it wasn't observed by a ground monitor. And we know that a lot of the places that don't have ground monitors are typically disadvantaged. So the 65 cities that were included in our study, but were not in this review, had a gross national income that was about a quarter of what it was for the monitored cities. So it shows that these satellite-based estimates can provide information on these disadvantaged areas. Next, we can look at the other things that the spatial information from a satellite can give us, which is things like comparing changes in different locations. So for example, we can look at the 20 largest cities in India, China, and the US, and compare that to the 20 largest fossil fuel burning power plants in these countries. So we know from the previous slides that most cities saw large decreases. So the blue are the cities, large decreases during lockdowns. In India and China, the areas around the power plants also saw large decreases during lockdowns. But we can contrast that with the US, where it was much more variable. There were some places near power plants that did see big changes, some places that did not. And that indicates things like changes in electricity demand, different fuel types, different emission controls, but it goes to show that there's spatially resolved information that can be taken from these satellite-based estimates to look at how changes differ in regions and between sectors. Here's another map that kind of demonstrates the kind of information this can give, where we're looking at the Atlanta region and comparing April in 2020 to April in 2019. And of course, like qualitatively, we heard a lot about how cities and the downtowns, the air seemed much cleaner. And the downtown core Atlanta is right around here, where all these roads intersect, the black lines of the roads, major roads. And so in the downtown core, yes, we did see lower concentrations, but the biggest change was actually down around the airport. Again, not really that surprising. It's the busiest airport in the world, and there wasn't a whole lot of air traffic going on. But we also saw really large changes in areas near these large coal power plants as well. And so our satellite-based estimates are able to show this spatial information in a way that you wouldn't be able to get from a ground monitor in the city. And it's going to be really important from an exposure estimate perspective, because it turns out in this measured domain, or in this map that we're showing, there's roughly 1.2 million people living in one of these grid boxes that had an NO2 change of more than 40%, but also another million people that were living in a grid box where NO2 changed by less than 10%. And so there's a lot of variability within a city in terms of how the lockdown impacted their air quality. And it turns out that Atlanta is not unique in this aspect. A lot of the cities that we looked at around the globe had similar sort of intra-city variability. So this is showing some of that variability both in an absolute sense and a relative sense. I can kind of consider these like box and whisker plots, where this represents kind of the median population exposure and then the different percentiles. So for example, if you look at a city like Paris, the median change in NO2 exposure is around, I don't know, 50%, but there's roughly 1 million people that saw a change that was more than 70%, and a similar amount of people that saw a change less than about 25%. So there's a lot of variability. And if you had 1 or 2 ground monitors in the city, you'd never be able to capture all of this information. So it can provide some really useful spatial information about the gradients in NO2 within these cities. And so that's where I'll stop from here. So I just want to say that these satellite-based estimates provide this spatial information that you can't get from ground monitors, and that there's some really interesting inter-country, inter-city variability. But in general, we saw significant changes in NO2, significant decreases during these COVID lockdowns. And I'm happy to take any questions about that.
Well, thank you, Matt. Lots to think about here. And I see applause appearing across the screen. So we'll open it up for questions. I didn't see any. I'll check the chat again. I don't see any there. So I see Taylor has the first question.
Hi, yeah, I actually have a couple questions, but they're kind of related. So they're both about the first half of the presentation, and specifically about when you talked about the geographic scale that you're working with the OMI and tropomi observations, and then using the geochem model. I didn't really understand why you needed to take that algorithmic approach you took to upscale, or I guess downscale, the geochem model to match the tropomi observations. I'm only passingly familiar with these grid-based models, so maybe you can answer for me why you couldn't just run geochem at a finer resolution.
Sure. Yeah, you could. You can run models at various resolutions. Yes, but the computational time can get very expensive, and so trying to think about how long it took to run these models. But if you want to look at global NO2 concentrations, if you want to run a global model, like we run at 2 by 2.5 degrees, and it takes to run a year, it would take you, I don't know, weeks to months to run a year's worth of that model at that coarse resolution. So every time you make that resolution finer, you increase the time it takes to run the model. It just becomes computationally too expensive. And so that's why we typically start with coarser resolution models. I will say that there's been some recent developments on the geochem front since this work was done. There's now, I think I have a picture. There's now a higher resolution model or a high performance model of geochem that runs on a kind of a highly parallelized system and is able to run at much higher resolution. And so in the future, we'll be able to use this model, but this is kind of a recent development. So this is just from a very recent paper showing this new simulation. You can see that the new model is able to better resolve these things. So we could likely get better estimates using these newer models, but at the time, this model was not available. This high performance version was not available. And so we kind of were limited by the computational time to run a global model. But you're right, a finer resolution model is preferred, and in the future, we'd hope to go in that direction.
Yeah, I totally understand the computational restrictions. That kind of leads me to my second question about these spatial resolutions. You talked about using tropomi data from like a few years average and then scaling 10 kilometer by 10 kilometer and 1 kilometer by 1 kilometer, so then you can back propagate that through the old OMI data. Wouldn't that intrinsically carry the statement that you are assuming that all of that historic OMI data had the same gradients as whatever tropomi data you use to do that propagation? Aren't you, by doing that, aren't you saying that you think the gradients have never changed?
Yes, which obviously is not necessarily true. If you have something like a new emission source popping out of nowhere, like you built or you tore down a large coal burning power plant, then that could change the distribution. So you're right, that is an assumption we make, and it's not a perfect one, but in a general sense, like the cities are roughly in the same places they were before. That hasn't changed. Like the major highways typically don't move like really far away. So it ends up being a pretty good assumption to make. If you have something like a large power plant that gets torn down or something like that, remember that we're using the we're essentially using the spatial information from tropomi to kind of redistribute what OMI sees. And so if there's a power plant now that wasn't there in 2005, tropomi might try to redistribute the NO2, but if there's no NO2 there, there's nothing to redistribute. And so in a lot of cases, it doesn't end up having a huge impact on things. And it's not likely to be a huge source, although obviously there will be isolated incidences where something really drastic did happen where maybe you might have a problem. But generally, I don't think that's a huge concern, but that is a good point.
All right, thanks.
Other questions?
Yeah,
Joel?
I have a question. Thanks, Matt. A very nice and a very comprehensive study that I can get some of a broad, picture of the what happened in the worldwide during the COVID-19. It's because we mostly have some focus on the very specific site, but I never seen the kind of some global-wise, scale. I have a question about the some spatial, the variability of the reduction. So you show that the NO2 reduction is around 20%, but it will be a plus minus 20% across the world, or also across by some cities, right? So I just wondering what source of this reduction. You show that some of near some cities nearby power plant, or some cities very the traffic dense area, also some cities across by some airports, something like that. But some policy the development. So if we want to reduce that the NO2 emission by 20%, so what's your recommendation to reduce the number of traffic by half, or some of a number of power plant using the coal burning? What I mean, it's kind of I want to see some of your opinions. What's the best the approaches we can learn from this COVID lockdown?
I mean, this is getting a little outside of my scope, but yeah, we consider NO2 to be mostly a traffic pollutant, with the exception basically being airports and power plants. Like those are kind of the heavy hitters for NO2. And so from an NO2 perspective, reducing traffic emissions is what's going to have the biggest impact. And a lot of this kind of inner city or within city variability, a lot of it tracks to where the heavy traffic areas are. And so that's kind of the main thing driving these differences that we see.
Let me follow up on that. So you showed us some CO2 data, which was interesting to compare with, and it showed the fairly substantial drop for air flights and certainly for transportation as well. I'm wondering how those estimates, which I think if I remember that paper, were either Canada or North America, how those estimates compared with the NO2.
Yeah, I didn't make many comparisons between the NO2 and the CO2 data. So I can't speak to any work that I did, but I have seen, for example, there are groups that have been using tropomi NO2 observations as kind of a proxy for estimating CO2 changes, and they found really good relationships, but that's not work that I've been doing. Okay,
fair enough. And let me go back to let's see, Jeff's got a question after, but I'll jump in. The assumptions that Taylor was discussing. So and I realized I didn't quite understand something about how geochem is being used here. So how much spatial variability within a, say, 10 kilometer by 10 kilometer would there be in the vertical gradient? I'm trying to think of whether that is the thing that's varying, or as you discussed it, whether it is assumptions as to where the sources are, where there's a power plant, for example, within that. So it's the geographic, not the meteorology. Which one of those is geochem trying to cover, or is it both?
I'm not sure I understood your question. So
Okay.
over,
So, go ahead.
oh, I was going to say, over a 10 by 10 kilometer area, you could have some pretty drastic differences, especially if you have like a small city and then rural area or really rural areas outside of it, or sharp changes in population density and traffic and things like that. So there can be some very large differences over that scale, but I'm not quite sure what.
Yeah, certainly. Yeah, I was trying to differentiate between, we'll call it the land use, because we often do this with land use regression, where you have where sources are located, and then the second part to it is the meteorology in terms of how they mix. And
Right.
my impression when you were doing the subgrid analysis is that when you backcast, you're assuming that the spatial gradient stays the same over time, and I agree that makes perfect sense. Cities don't move, but then how much does the vertical gradient or the air mass factor change within a 10 kilometer by 10 kilometer box? Is that really something that we have to worry about? And my impression was that that's what was being done by using this subgrid approach.
Yeah, that's a good question. Yeah, so I guess like by using the satellite to help us do that downscaling is kind of correcting for both of those in a way, because we allow the satellite to tell us where we should shift the model profile. And so, a model grid box is pretty coarse. There could be a lot of things going on in a model grid box, and it's not going to capture these fine scale things very well at all, really. But by allowing the satellite to kind of shift NO2 around vertically and horizontally, it does correct for a lot of these things. And we actually see that if you apply, if you don't apply, all right, let me put it this way: if you don't apply this satellite constrained scaling on the model, and you just kind of try to use the model column to surface relationship to estimate ground level NO2. Oh, I might have a graph for that too. You find that do you have a graph? Okay, you find that as the model concentration gets worse or gets coarser, the agreement between your satellite-based estimate and the ground monitors gets worse, because your model's getting worse and worse at representing what's going on. But if you do use the satellite-based constraint, you see much less sensitivity to the model resolution, because the satellite is helping to kind of fix those biases. And so that's how we're able to use such a coarse global model and still get a pretty good 1 kilometer map, because we're letting the satellite kind of fix some of those problems.
Great, that helps. I'll say we're just at the hour, so I'm going to pass it to Jeff, but we have time. We'll try to fit in one more question. So
okay, yeah. Thanks, Greg, and thanks, Matt. And sorry I couldn't be at the beginning. My question is more broadly just about the lockdown changes and the effort obviously it takes to do all of this analysis, which is tremendous, and focusing on sort of the strict lockdown periods. And we know that certainly COVID's been going on and on for a long time now, so things are becoming less strict, more strict, and so there's sort of a longer temporal profile. And where might the world be at in terms of sort of following this temporally, in terms of the changes and insights you might get from it? Are you continuing to follow this yourself? I know you've certainly changed your job, or are others, working on this to gain some more subtle insights?
Yeah, this is not a thing that I'm working on anymore, but I have seen some people kind of continuing to look at how this has been changing, and I don't have to tell you that we're more or less at business as usual now. So there were some really large changes early on, the beginning of the pandemic, but even at the end of this kind of 6 months that we looked at the first start, things were already kind of approaching normal again. And I doubt that we would have seen very many significant changes after that. Because remember, you know, we have to have, the change has to be large enough to make a signal that's large enough for the satellite to pick it up.
Yeah.
And as the stringency of these lockdowns get weaker and the adherence to them gets weaker, then, you know, your ability to monitor that from space is going to be hindered.
Mm-hmm. Mm-hmm.
Yeah.
Yeah, I mean, in terms of those researchers asking about health benefits during those short time periods, and probably dragging out the time longer to see more of those changes might benefit the health researchers, but yeah, not as good as they were. Thank you.
Yeah.
Well, we are at just about 4 minutes after, so I do see a final question from James, but unfortunately we're not going to give him time to ask it or give you time to answer it. So maybe James, you can follow up with Matt offline.
Yeah, go ahead.
Want to thank Matt very much for fascinating seminars, some great work, wonderfully presented. So thank you very much for joining us, and thank you to all who joined us today. And we look forward to seeing you at future Socaar seminars.
Hey, thanks.
Have a great day.
Thanks very much.
Yeah.